So thank you for the presentation, Chairman. As the Chairman just said, my name is Diego Infante-García, and I'm from the Technical University of Valencia in Spain. And the topic of my presentation will be the characterization and the fracture of cortical bone at the microscale using different numerical modeling approaches. So this slide shows the contents of my presentation. I will start with a short introduction of the topic, explaining the main motivation and objectives of the work. And based on these objectives, I divided the presentation into two main parts. On the first part, I will talk about the toughness characterization of one of the constituents of the bone at the microstructure. And then I will explain the methodology that we have employed to simulate the the microfracture of the cortical bone. I will finish with the main conclusions. So let's start with the introduction. Let me just start explaining a little bit about the bone hierarchical structure that it possesses. From a macroscale point of view, bone can be divided into two main tissues, which is the compact bone, or the cortical bone, and the spongy bone or the cancellous bone. Being the compact bone, the more dense bone that we have on the outside of long bones. If we take a look at the microstructure of the compact bone, we can observe that we have these lamellas that are concentrically arranged surrounding the Haversian canals. Each of these concentrical lamellas and each Haversian canal forms, which is the main structural unit at the microstructure, which is called the osteons. And as we can see, we have like several of these columns, which is called the osteons, inside of our compact bone. Just to remark that the Haversian canals are necessary in order to run all the vessels and the nerves that we are going through the bone. If we take a look of the cross section of the compact bone, this is a micro photography. We can observe here the Haversian canals, or these notches for us as engineers. And then we can observe all the arrangement of the lamellas forming the osteons. And there is another very important part, which are the boundaries of these osteons, and it's called the cement lines. These cement lines are weak interfaces that goes between osteons and the interstitial matrix, and these weak interfaces act as a toughening mechanism in the bone, in the apparent bone toughness, because usually cracks are preferentially grow through these cement lines, and also is a barrier to protect the breakage of the Haversian canals and all the vessels and nerves. So why is important to study bone fracture? Well, due to the elderly population, degenerative diseases in bones are a major problem today. And understanding bone microfracture is a crucial task to defining the fracture risk. Here I'm showing just two micro images of a healthy bone of a 32 years human, and then a very osteoporotic bone. As we can see, the microstructure changed significantly, and most of the literature regarding the characterization of these diseases are focused on the morphometric quantification, and the constituent mechanical properties is very, very limited. And just apparent properties are usually calculated. So in this work, we're going to focus especially on the characterization of the strength and the toughness of these cement lines that I previously mentioned in the previous slide. So two main objectives are derived in this work. First of all, the characterization of the fracture toughness and the strength of the cement lines, which we are going to use an approach based on the framework of finite fracture mechanics, and then the simulation of the crack propagation in cortical bone at the microscale, in which we are going to use the cohesive zone model and the phase field model. So let's start with the toughness characterization of the cement line. First, I'm going to explain the experimental test that we have used. We have performed 3-point bending test of notch-ovine cortical bone samples, very small samples. First of all, we cross the diaphysis of the tibia of in tibias of approximately 1 millimeter thickness. Then we perform the test. We perform 4 tests, and then we also notice that we produce a notch of around 0.5 millimeters in the samples. We record the forces, and we measure the displacement. Also, we perform a staining process, which is helpful to reveal the microstructure of the cortical bone, and we can see more clearly the osteons and all the Herpesian canals. Second, as I said before, we are going to use finite fracture mechanics in order to assess the failure of these cement lines. And particularly, we are going to use the couple criterion, which is originally proposed by Leguillon in 2002. And this couple criterion imposes the simultaneous fulfillment of 2 conditions. The first condition is a stress criterion, and the second condition is an energy criterion. And these 2 conditions need to be fulfilled along a characteristic length. I think that's the reason that they call like finite fracture mechanics, because it's always through a characteristic length. So the stress condition is just very simple. Here is a sketch of our problem. It's just a notched component under a remote stress, and this is the proposed characteristic length. So we can, the stress criterion says that the stress along this all characteristic length needs to overcome the tensile strength, no? Or maybe if you're in a multiaxial stress state, is a function of the stress tensor. Here we can see a representation of the stress criterion. So basically, you as long as you are further away from the notch, there is a monotonic decreasing stress. And this is the region where the stress criterion is fulfilled. So it gives a upper-lower bound of the characteristic length. And then we have the energy criterion. And the energy criterion is an interpretation of the Griffiths principle, but incrementally. In this way, you need to have enough energy to create a crack along the characteristic length. In this case, you use the incremental energy release rate, and you have this inequality. And here we have the blue line representing the energy criterion. In this case, because at the beginning we have no crack, basically it starts from zero, and it's a increasing monotonic function. And when both criteria are met, you have the characteristic length and the critical load. So basically, you propose 2 systems of equations in which you solve the critical load at the characteristic length of the structural characteristic length. So first of all, we require to calculate the stress along this characteristic length, and we need to calculate also the strain energy release rate along this characteristic length. And to this end, we have used the finite element method. We have performed image segmentation from several tests, and we have segmented and considered all the osteons and just close to the region of where the crack is likely to happen. Then we have calculated just at the critical load with a simple linear elastic analysis, the stresses along the interface, and we just need to rotate these stresses to calculate on the local coordinates oriented with the interface, and we can calculate the normal and shear stresses at the interface, and this is what it looks for one of the examples. So we can see here that this, as the example previously explained, we have a monotonically decreasing function. However, in this case, it's a bit different because the interface is not straight and is thinking. So maybe it's not at the end. It's not like completely like monotonically decreasing. On the other hand, we have to calculate the energy release rate. In this case, we have perform linear elastic analysis, but we have performed incremental linear elastic analysis. So in this case, we just need to release each of the nodes. We have performed successive simulations, and we just need to calculate the variation of the total potential energy divided by the crack length. So we can calculate very easily the energy release rate. And again, in this case, it starts from 0 because there is no crack at the beginning. And once is monotonically increasing, but again, because the crack is kinking, you can see that the shape is a bit different from the previous slide. So once that we have the critical energy release rate, and we have also the stress interface, usually when you apply the Couple criterion, you want to know the critical load and the characteristic length. However, in this case, we have a finite fracture mechanics space inverse problem, because what we want to calculate is the toughness and the strength of the interface. So we have employed multiple objective functions and an optimization algorithm to obtain these, to calibrate these properties. And we have applied some restrictions to reduce the number of possibilities. And this has been employed for several tests. And after all this work, we've been able to calculate the normal stress, the normal strength, the tangential strength, and the toughness of the interface. Note that in this case, we have used a quadratic criterion for the interface stresses to consider also the shear stress. So once that we have characterized our interface, we've been able to perform the microcracking simulation of the cortical bone. And I'm going to explain this very briefly because I don't have a lot of time. But we have used the cohesive interaction surface for to modeling the damage in the interface. And here we have used, again, a quadratic traction initiation criterion using the properties that we have calibrated in the first part of during the first part of the presentation. And then we have used a bilinear traction separation law using the toughness of that we have calculated previously. And for the fracture of the interstitial bone and the osteons, we have used the phase field model. We have performed this simulation in Abacus. So we use a user subroutine developed by Naviditerani et al. And very briefly to explain, phase field is a variational fracture model in which you minimize the total potential energy considering the crack path. However, the sharp cracks are smeared over a characteristic length that is, in our case, it's just a numerical parameter that we have defined as smaller as possible, compatible with the dimensions of our problem. So these are the results of the simulation. On the left side, we have a video, and on the right side, we have the results of the experiment. So we can see here how the crack tends to grow preferentially through the cement lines, as we observe experimentally. And here, as I commented before, the crack never grows to the Haversian canals, and it's just a way that our bones has to protect these channels. And also, this means that it increases the apparent toughness, no? And if we take a look of the critical loads and we compare with the experimental results, we can observe that there is quite a good agreement on the critical loads that we have obtained for this test. However, the damage evolution is not, we didn't capture yet, but well, this is just some preliminary results that by now, we are very happy to show. And just the main conclusions. So we have proposed a methodology to calculate the strength and toughness of the cement lines in the cortical bone using a finite fracture mechanics space inverse problem. And also we have been able to simulate the complex microcracking trajectories in cortical bone using cohesive zone models and phase field model. And well, future work, we have a lot of future work that is coming from the 3D problem, the introduction of the mode 2 toughness, and the characterization of the constituents of the microstructure of the bone. Also increasing the number of tests that we have performed, because just performing 4 tests and it's not as much as necessary to validate our work. So thank you for your attention.